Welcome to MET 200 Manufacturing Processes and Material. This is Dr. Hamid Isazadeh. In this lecture, we continue talking about metal forming process. It's lecture 14. In this lecture, we um, talk about forging operations. We talk about extrusion and wire bar drawing, um, which are part of chapter 18 in the book. Forging is a deformation process which the workpiece is compressed between two dies. And this is one of the oldest metal forming operation. It started around 5000 BC. And the products, we have a variety of products in this process. We can have engine, crankshaft. We can produce connecting rods, gears, and turbine parts. You see in this picture um, the steps involved in forging knives from this part going this way. So this is the final workpiece. And here this picture is the landing gear component for aircraft. And this is the machine, forging machine. You can compare the machine and get the idea how big it is when you look at that machine and compare it with the person standing next to the machine. In the rolling operation, we can produce continuous plates, sheets, strips, or various structural cross sections. But in forging operation, we can produce discrete parts. And the metal flow in the die in the forging process can be controlled in a way the the grain structure in the forging process is unique and it's different from other manufacturing processes like casting and machine process. For example, in this picture, we have three processes and they have a grain structure for each process. For the casting, we have a uniform grain structure, and this one the grain are aligned this way. Depends on the where the machining process is done. And here we have the grain structure in the forging process. So once the part is done, the grain distribution will look like this structure in the forging process. The forging operation can be performed in two temperature environment, cold or hot, and each one has its own advantages. If we do the forging process in the hot or warm condition, we have advantage like reduction in strength during the process. The strength of the part is going to be lower, so you will need lower load for the process. Also, the ductility of the work metal is going to be higher, so the chance to have failure during the process is going to be less if we perform the process at higher temperature. But if we do the process at the colder temperature, like a room temperature, the advantage is that the strength of the part, the produced part, is going to be higher. So that is the very good advantage for the parts in the cold forging process. The forging operation also can be done with a gradual pressure or impact. And if we use impact load, the machine is called forging hammer. But if we use gradual pressure, then the operation or the forging machine is called forging press. We have three forging operations based on the degree of flow in the work metal. The first one is called open die forging operation. This one, as you see in this picture, the work is compressed between two flat dies. That allows the metal to flow laterally with minimum constraint. The second one is called impression die forging operation, where the metal flow is constrained so that flash is going to be created. This is flash, as you see this the left side of the part and the right side of the part, and the dies has a shape, it has um, impression, and this flash is excess metal that we have to trim off that part from the workpiece. So this has to be trimmed off. The third one, which is the flashless forging operation, which is similar to impression die forging, but the main difference is that it doesn't produce flash anymore. Among the three operations that I mentioned before in the previous slide, the first one is open die forging operation, where the workpiece is going to be produced by compressing raw material between two flat dies. It is similar to compression test, and the workpiece can be, cylindrical cross section, and it's compressed along its axis. And in this process, the formation operation reduces height and increases diameter of the workpiece. And it has other names. It's called upsetting or upset forging process. This schematic, as you see in this the slide, shows the three steps in the open die forging process. And here we have the initial height. This is a partial height, and this one is the final height. The process may have friction, may have no friction. If we don't have friction in the process, we use lubrication on the surfaces, then a homogeneous deformation forms so that the radial flow is uniform throughout the workpiece, and that true strain can be calculated by this equation. In the open die forging operation, we may have friction, and that friction can affect the shape of the final part. Here in this schematic, as you see, the different steps of a process when we have friction, and the result is different from the previous one. We have a barreling effect. It happens mostly when we do process at high temperature in the it's called hot open die forging operation, and because outer surface of the workpiece is cool and the inner surface here is hot. So because the outer surface is cold, it resists deformation. The next operation is called impression die forging, where the work part is going to be produced by compression. Um, we have dies in this operation, like this picture, as you see, this is schematic, the dies with the inverse of desired part shape. This operation provides some flash as I said before, it's the excess metal that has to be removed, it has to be trimmed off. But the flash serves an important function during a compression, because as flash forms, this part, as flash forms, we have friction over there. The friction resists against the metal flow in that gap. So what happens, because of that friction in this area, the gap, the metal is gonna stay in this cavity to fill the die. In a hot forging operation, when the temperature is high, the metal flow is further restricted because of the cooling against the die plates. Here are some advantages and limitations of the impression die forging operations. First, let's look at the advantages. It has a very high production rate. It has some waste, but that waste is less. And we have great strength. The strength is high in this operation. We can manipulate, we can design grain orientation in this operation. So you want to have a favorable grain orientation, then this is the process that we should use. Limitation, it has some limitation with the close tolerance. As I said, since we have flash in the process, in the workpiece, normally we need some machining, and the machining is required to achieve the accuracy and features that we need. In the flashless forging operation, again we have compression of the workpiece, but in this operation the cavity does not allow for flash. So the starting work volume must equal die cavity volume within a very close tolerance. The process, in this process, it's more, in terms of control, it's more demanding comparing with the impression die forging operation. And this process is best for simple geometries like symmetrical cylindrical shape. These are best part for a flashless forging operation. And it has other names that are interchangeably used. It's called precision forging operation. In this schematic, we see different 3 steps in the flashless forging. Here we have just before contact with the workpiece, and then the second one we have partial compression, and the last one we have final punch and die closure. The forging operation have to be done with the forging hammers, and forging hammers are 2 types. One is impact hammer, the other one is called press. Here the impact is going to be generated. For example, if we are using gravity drop hammer, we have impact energy which is coming from a heavy ram. That heavy ram fall in the certain amount of space and generate that impact energy. The next one is a power drop hammer, where a ram is going to be accelerated by pressurized air or steam. The problem with the um, drop hammer is that the impact energy transmitted through anvil into the floor of the building. So the building should have a good foundation to resist that impact, and it's mostly used for impression die forging processes. And this is the um, schematic of the drop hammer, different part of it. You see, this part is ram, which goes up and down, and we have piston here, and this is anvil where the part is going to be located, and then it's going to be compressed between the ram and anvil. This picture shows the actual drop hammer. As you see, it's pretty big comparing with a person standing next to the machine. And this is the anvil, this part, and this is the ram which goes up and down, and here is the part located between the um, anvil and the ram. Then the second type of forging hammer is called forging presses, where the gradual pressure is going to be applied to accomplish that compression operation. In the forging presses are three types. They can be mechanical press, which converts a rotation of a drive motor into the linear motion of the ram. The next one is hydraulic press, where we have a hydraulic piston that actuates the ram. The last one is a screw press. We have a screw mechanism that drives the ram. There are other deformation processes that are related to forging operations that here we will talk about them one by one. The first one is offsetting, then we talk about heading, and then the last one is called swagging. We use offset forging process to form head on a bolt. It has several steps, 4 steps, as you see in this schematic. The first step is this one, where the wire stock is fed to a certain distance. If we have a stop here, the part stops there, and then we have a gripping dies, this one, that moves toward the part, and it holds the part firmly. And the step 3, we have a punch that moves toward this wire, and it creates a head like this shape. This process actually produces a lot of parts, as you see, nails, bolts. These are the parts that are generated by offset forging. There is also another process called heading forging, and this heading forging is similar to offset forging. In some cases, we use open dies to create a nail like this form. They can create other form, other shape, like a round head, um, like a carriage bolt head, this one. The next operation is called swagging or radial forging. This operation reduces solid rod stock. So as you see, this is the part that moves into the die, and the die goes up and down, so it's not steady. It somehow work like a hammer, and they reduce the diameter of the tube or solid rod stock. What is extrusion process? Extrusion is a compression forming process which work metal is forced to flow through a die opening to produce a desired cross-sectional shape. And it is very similar to squeezing toothpaste out of a toothpaste tube. In general, extrusion is used to produce long parts with uniform cross sections, and it has two types. One is a direct extrusion, and one is indirect extrusion. And here we have a schematic in this picture of this process, where you see we have a ram that moves this way, and this is the workpiece, work billet, and the ram push this material, and it has to go through this die opening, and the cross section of that part is going to be similar to this die opening. In the direct extrusion, also we call the forward extrusion, the direction of the part, as you see, it's this way, and it is the same as the direction of the ram. Because they are in the same direction, they call direct extrusion. And the starting billet cross section normally in this process is round, and the final cross section shape of the extrudate, this part, is determined by the die opening shape, which is this area. And normally there is a small portion of the billet that remains in this container, and it's called the butt. This problem can be addressed by adding additional material that we don't need it, and then it can be cut from the final part. So this way you can reduce the waste material. Here we have different shape that we can produce with this extrusion process. In indirect extrusion, which is also called backward extrusion or reverse extrusion, we have a ram that penetrates into the work, and the metal is forced to flow through the clearance in a direction opposite to the motion of the ram. So the ram is moving this way, and the part flow this direction. Direction is opposite. As you see, it's not the same. Because the direction is opposite, it's called a reverse extrusion. There are some limitations. Two of them is that indirect extrusion is imposed by the lower rigidity of the hollow ram, and it is difficult to support the extruded part when it exits the die. In this slide, we have advantages of the extrusion process. Variety of shapes are possible in this technique, especially when we are dealing with hot extrusion. The limitation is that the part cross section must be uniform throughout the length. And grain structure and strength of the part is improved. You can improve the grain structure in cold or warm extrusion process. We can have close tolerance. This when we are working with cold extrusion. In some operation, we have little or no waste of the metal. Extrusion process can be performed at a hot temperature or a cold temperature, and it depends on the work metal and the amount of strain that we need during the formation. For example, aluminum, zinc, magnesium, These are some metals that hot extrusion is preferred over cold extrusion. And in the hot extrusion process, we have reduction of the strength in the metal alloy, so we need less energy to deform the work metal, and the ductility of the metal goes up, which permits more size reduction and more complex shapes. And hot extrusion normally is performed above the recrystallization temperature. What is recrystallization temperature? It's a temperature where the crystal lattice structure of metal becomes reoriented. So because of that, the metal becomes more workable and ductile. The cold extrusion, on the other hand, generally used to produce discrete parts. Sometimes we use impact extrusion word, which is used to indicate high speed cold extrusion process. There are some important factors in the extrusion process. One of them is the die angle. As you see in this picture, this is the angle between die and horizontal line. And in this picture, you see there is a relation between the force, the ram force, and that angle. So if we have a low die angle, for example, like this shape, then it increases the friction at the die billet interface. Because of that, high friction, we need larger ram force. On the other hand, if we have large die angle, it increases turbulence in the metal flow during reduction. Again, it increases the ram force. So as you see, the ram force goes up. So we have an optimum angle somewhere here that we have the lowest amount of ram force for that operation. The next important factor in the extrusion process is the shape of die orifice. The shape of die orifice affects the ram pressure, and the simplest cross-sectional shape is circular die orifice. As cross-sectional becomes more complex because we have more interface between the die orifice with the billet. Higher pressure and greater force would be needed. And this force can be calculated by a factor called a die shape factor Kx. And the Kx is the ratio of pressure required to extrude a cross-section of a given shape relative to extrusion pressure for a round cross-section of the same area. We have other extrusion processes like impact extrusion, where the punch impacts the workpiece rather than simply applying pressure to that workpiece. We have here in this picture forward extrusion, and this is backward extrusion. And the impact extrusion normally is performed at higher speed and shorter stroke, comparing with the conventional extrusion process, and it is used to make individual component or discrete component. And the impact extrusion is usually done at a low temperature, the cold extrusion process, and it can be done on a variety of material. And backward impact extrusion is most common one. The products we have with the impact extrusion is toothpaste tube and battery cases. Other extrusion process is called hydrostatic extrusion. One of the problems in direct extrusion is that we have friction along the billet and the container. If this is container surface and this is the billet surface, so we have that interface, and which causes friction. So this problem can be addressed by surrounding the billet with a fluid inside the container. And we have fluid inside the container, we can pressurize it, and then with the motion of a ram toward the die orifice, this part can be created with the shape of, with the cross section, a cross section with the shape of die orifice. This way, there is no friction inside the container, and the friction at the die opening is reduced. Because of that, the ram force is significantly lower than in the direct extrusion process. But there is a problem, there is a limitation. One is that it requires some preparation for the starting work billet, because we have to make sure there is no leaking in that area, so all the fluid stay inside the container. There are three types of defects in extruded products. The first one is called center burst or internal crack, which is this one. And this defect is an internal crack which develops as a result of tensile stress along the center line of the workpiece during extrusion process. If we have tensile stress during the process, that will end up internal crack. The next one is called piping, which is associated with the direct extrusion process. This problem can be addressed by a dummy block which has the same diameter, and that can stay here, then it can be trimmed off. The next one is called surface cracking, this one, and this defect happen when we have a high temperature at the workpiece, and that causes crack to develop on the surface. And we can address this problem by lowering the speed of the extrusion. If the speed is too high, then we have a high temperature, or we have a high strain rate, which generates heat. You know that if we have too much deformation, the deformation creates heat, and that heat causes a high temperature and then surface cracking. So we have to lower the speed, then this problem can be resolved. The next process is called wire and bar drawing. In this operation, if we have a rod or bar with a circular cross section, and the diameter of the wire is reduced as we pull it through a die opening. The difference between this process and extrusion is that the work is pulled through the die in drawing. However, in extrusion, the part is pushed through the die. So that is the main difference. As you see, the force is here. So we are pulling the workpiece. But in the extrusion process, the ram is located here and it's going to push the part on the left side. The drawing process can be performed at a cold temperature, at a low temperature, and it is frequently used for round cross sections. Here are some of the products of the drawing operation. We have electrical wire, we have wire stock for fences, coat hangers. All of them are produced by drawing operations. The next process is called bar drawing. This operation can be done on a machine called draw bench, as you see in this schematic. This machine has an entry table, it has a die stand, it has a carriage, it has an exit rack. And the carriage is used to pull the stock through the draw die. And the process is powered by a hydraulic cylinder or a motor-driven chains. And the die stand is often designed to hold more than one die, so that several bars can be pulled simultaneously through the respective dies. So far, we talked about wire drawing and bar drawing, and there is a small difference, and that is stock size. In the bar drawing, we have a large diameter bar or a rod stock, but in the wire drawing, we have a small diameter stock. The wire size is going to be around 0.03 millimeter or 1,000 of an inch, and the mechanics in both operation are the same, but the methods, equipment, or sometimes terminology are different.